If you look at the diagram that you have in your notes, this is why we call this topic conic section. So if you were to take a cone and intersect it with with planes at various angles, then you get a wide kind of variety of shapes. We are going to be focusing on 3 of those shapes over the course of the next 3 classes, obviously not including Monday. We're going to start with ellipses, then we're going to look at hyperbolas, and then we're going to revisit parabolas in this kind of new context of how they relate to the other conics. The good news is that at the very least at the front end of today, it's mostly just like definitions. Once you get a feel for this, it becomes very, very quick to identify what these things are going to look like, how they're going to behave. You just need to get it into the right form and know what to look for. So what I have here is an example of an ellipse. Ellipse is just kind of like a fancy word for an oval. And we are going to start out with a definition here. I have a couple of points labeled. We'll assume for now that our ellipse is centered at the origin. And for this first example that we're looking at, we have a horizontal ellipse, although that certainly doesn't need to be the case. We could have an ellipse that's like rotated by 90 degrees here. That would give you a vertical ellipse. So that would also be totally fine. And I have 3 kind of significant lengths that I have defined here as A, B, and C. And from the origin, you can notice that, we're traveling that distance in a variety of directions. I'm going to start off by defining this length C, which is maybe a weird place to start because it's like the points that aren't actually on the ellipse. But those are going to give us kind of context for what is happening here. These points are called the foci. And these are what are corresponding, in this case, to like C, 0 and negative C, 0. Again, not always, but for this specific ellipse, those 2 points are what we would classify as the foci, which is plural for focus. Okay. We didn't spend a whole lot of time working with circles this year for this particular class. But we have an algebraic definition for circles, which is essentially the set of all points that are a fixed distance from a center. So if you think about like every single point on the edge of a circle, it is a fixed distance r from the middle of the circle, from the center of the circle. And we get a very similar definition for our ellipse. The difference here, though, is while, yes, we do have a center, we don't have a fixed distance from that center. Obviously, the distance horizontally is a lot further than what we see with the distance vertically. But when we are considering our foci, we can construct a very similar definition to what we get for a circle. So I'm going to go ahead and define an ellipse here as the set of all points xy such that the sum of the distances between the foci and the point xy that we are considering is constant. Which feels like a lot, but actually it's not nearly as bad as it seems. So for instance, you'll notice here in the pink, I have drawn and labeled from my foci to a particular point on my ellipse, distances that I have labeled d1 and d2. And what this definition of the ellipse is saying is that it doesn't matter which point I pick, whether I'm comparing d1 and d2, or I picked a different point in blue here. and I've labeled those distances D3 and D4. It doesn't matter where we are on the ellipse. The sum of those distances, so in this case D1 plus D2, should match D3 plus D4 for any 2 points that I pick on my ellipse. That distance is always, the sum of those distances is always going to be the same. Okay. There's some really cool like geometric ways to draw ellipses. If you like take 2 points and like connect them with a string and use that to like trace out a shape, that will end up drawing an ellipse, and that's essentially saying what we have here. You can look up some cool like YouTube demos on that. They're interesting. Okay, so that's C. Let's now define A and B. We're going to go ahead and define A. Actually, A is equal to, not defined as, A is equal to the length of what we call the semi-major axis. What is a semicircle? Half a circle. So what is the semi-major axis? Half of the major axis, which is kind of what we would see. This distance here is half of the major axis. So the actual major axis goes from negative A to positive A in this particular case on that horizontal axis. If A is the length of half of the major axis, what is the length of the major axis going to be? 2A. Not coincidentally, but kind of a cool thing. This is also what this sum is equal to. Also equal to 2A. And then if A is defining the length of the semi-major axis, what is B probably defining? The other one, what do we probably call it? Semi-minor axis. Yeah. And we could say the exact same thing, right? So therefore, the minor axis would be 2 times B in terms of length. I want it to be known, and we'll see this when we actually get into like the definitions here for the actual equation. Um, A is always going to be the large one. B is always going to be the small one. So A is always major. A is always the large axis. B is always the minor, is always the small axis. And depending on whether that axis, that large axis, is horizontal or vertical, we'll see that manifest itself in the equations that we look at. It's pretty easy to tell, but I want you to kind of lock into your head, A is always bigger than B, right? Major, always bigger than minor. And that's how you can tell, are we horizontal or vertical? Okay, from this, actually, and from this alone, we can go ahead and figure out an equation to calculate where C should be, that distance C. With one additional kind of prompting here, which is that C is always symmetric about the center. So we always travel, when I'm trying to figure out my foci, I start at the center and I travel C to the right and then I travel C to the left. And that gives me what those would be, where those would be located. Or depending on the orientation, C up or C down. Okay, so in green here, I have drawn another kind of set, another point. In this case, I'm connecting my foci to what we call the co-vertex. So the vertices of this particular ellipse correspond to the points on my ellipse that are on the major axis, and the co-vertices are the points that fall on the minor axis. We can go ahead and define that. So vertices are points of ellipse on major axis, and co-vertices are points of ellipse on minor axis. Okay, so I want to consider this distance, which we know is fixed. What is the sum of my green distances here? 2a, right? We said that the sum from foci to point plus the other foci to point is always going to be 2 times a. What you'll notice here is we actually kind of trace out, not kind of, we do, just trace out a right triangle with each of those distances, right? We've got a right triangle here. What is this vertical distance? What is this leg? That's just B. What is this vertical leg? That's C. That's the distance from center to focus. Okay. And so then the question becomes, if I want to know what C is, I've got this right triangle. All I need is this green distance here. Well, I know the sum of my green distances are 2a. And so what should this green distance be, knowing that our minor axis point is kind of situated directly above the center of our hyperbola, or of our, not hyperbola, of our ellipse? It's just equal to a. The green distances are equal. If both green distances together make 2a, one green distance is just going to be a. And so what does that give us according to the Pythagorean theorem? So what are our legs and what is our hypotenuse? B squared plus C squared is equal to A squared. And we said the point of this was to solve for C. I get that C should be the square root of A squared minus B squared. So the distance between center to focus is going to be Pythagorean theorem, square root of A squared minus B squared. Where again, in this case, A is the hypotenuse, B is our one of the other legs. Last thing that I'm going to mention is that the foci are always going to be located, well, there's a little bit of an asterisk here. For ellipses, the foci will always be located along the major axis. I say for ellipses, you get a different shape when you move the foci to the outside of your shape. You get something slightly different. But for our purposes, we'll say that the foci, at least for today, we'll mess with that on Tuesday. Foci are located along major axis. It's a good day. My brain's doing well. I can spell the word along. Along. Yeah. I don't have lecture recordings on this. I haven't taught this in like 3 or 4 years. So were they helpful? Good.
I thought I don't know. I didn't think the vector stuff was too hard.
It's really not. The physics application stuff is tricky, but like the stuff that's like on the test it's really not. That's not bad. I mean, it's application of the 8.8 stuff. It's supposed to be hard. So if you have questions about it, I'm happy to like take a look at those. But it was kind of just like a fight through it. I don't know how I'm grading it. I don't know if it's like part completion, part going through and checking like specific ones. That's normally how we do like the web assigns. So not sure. Not sure. All right. Questions about the features of our hyperbola. All right. Yes, I'm doing well. Ellipse. Questions about the features of our ellipse. We're doing great. It's only when I make these mistakes when we hit the record button, right? Questions. Okay. Let's look at the equations. The good news is that the equations are going to give us basically everything we want. For now, I am still going to make the assumption that we're centered at the origin. The change between centered at the origin and not centered at the origin is very, very simple. So if we can deal with centered at the origin, then one quick adjustment and we're going to be good elsewhere. If we have a horizontal ellipse, which you will be able to tell basically instantly by determining which axis is major and which axis is minor, then the equation to the ellipse is x squared over a squared plus y squared over b squared is equal to 1. Where a is the length of the major axis, notice in this case corresponding with the x value, which is why it's horizontal, and b, the length of the minor axis corresponding to the y value. Hence why we will end up with a horizontal ellipse because that distance is a little bit more stretched out. Versus if I had a vertical ellipse, well, what would this look like in order to make it so that I have a longer y value? What would you do here, Sean? You just swap the a and the b. So in this case, x squared over b squared plus y squared over a squared is equal to 1. And again, how you determine am I looking at a or b? A is just bigger. A is the one that is large. Always going to be like that. Yep. They could be the same. What kind of shape would we draw out if they were equal? It would draw out a circle. Yeah. If A and B were the same, so normally the equation for the circle is x squared plus y squared equals r squared. If you divide both sides by r squared, you get exactly that. X squared over r squared plus y squared over r squared equals 1, where again, that r is telling you the horizontal distance and the vertical distance. In this case, they are the same. Super good question. Let's look at an example. So first example that you guys have on your notes, I've got 4x squared plus 9y squared is equal to 36. What would you guys do in order to get the equation that we have here into the ellipse form that we see above? What did you say, Carson? I liked your idea, which is why I'm picking on you. Yeah, notice that for both of our equations, regardless of where the minor axis and major axis are, we are always offset from 1. So like with our quadratic, how we like to be equal to 0. In this case, we like to be equal to 1. And so dividing both sides by 36, I think is a great way to go. I get x squared over 9 squared, or sorry, not 9 squared, Freudian slip, over 9 plus y squared over 4 is equal to 1. What then are going to be our values for A and B? A is going to be 3 and B is going to be 2. How can I tell which one is A and which one is B? A is the one that's bigger. But we do have a piece of information here that is important. Which one is going to be horizontal distance and which one is going to be vertical distance? A is, we said horizontal. How did you figure that out, Ben? Yeah, because this is going with the x-axis. And so A should be horizontal. And then therefore B is going to be vertical distance. Yes, I got it. Sure. This was 6, 5. Or sorry, 8, 5. Did I just hear 10 points off of Tess? All right. Password. Password is Demal. Yeah. And show work.
Right now,
Yeah, all right. And then yes, Ishan, give me like 30 seconds to, I mean, not 30, give me like 10 seconds to add you. Demav. While we are here, what would our value of C be? How are you doing this? How do we find C? A squared minus B squared, take the square root. That gives us, I get the square root of 5. Well, he took the square root of the other side. Not a bad idea, but just remember it's coming from Pythagorean theorem. A is our hypotenuse, B and C are our sides, square root of A squared minus B squared. All right. And that is basically everything we need in order to graph this. Technically, we didn't need C, but I could reasonably ask you to find that. Yes. That's intense. Penalty kick. It's like that is the like truly like I don't even know how to describe it. It's a very cinematic moment. That's a very cinematic moment for them. But don't you how would you describe it? I feel like cinematic. Intense is good, but like it's the moment you would get to at the end of like a movie, you know? It's very what? Very broad. No, I just read a lot. Yeah, you should just read more. All right. In this case, we are centered at the origin. We haven't looked at an example where we're not. So for now, I'll just hand wave that and say we're centered at the origin. And A, we said, is describing a horizontal distance. So we are going to travel 3 to the right and 3 to the left to find our vertices. In this case, these would be the points 3, 0, and -3, 0. And then along the minor axis, we are going to travel 2 up and 2 down. And then you just connect the dots, which I'm bad at, so I'm going to cheat with the fact that my technology will autocorrect. Look, 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 look. It's going to autocorrect for me. I know. So it is. So the major axis goes from end to end. So if A is 3, what's that total length there? Would be 6. Yep. Great question. So these are our values for, and unfortunately, this was slightly. So Mary asked a really good question here, which is where does the focus tie in? And the answer is the focus is the distance from the center along the major axis to the foci. So the value of C, sorry, I should say, is the distance along the major axis to the foci. So in this case, traveling by root 5. Do we know exactly the value of root 5? No. So I'm just going to use the fact that it's probably slightly more than the square root of 4. So a little bit past 2. I get one focus here and one focus here. This would be the point. So my foci would be located at root 5, 0 and negative root 5, 0. And again, those aren't like on the ellipse, but those are the points from which, if I do these distances, that that is fixed and is equal to 2a. All right, questions with our first example here. How's this feeling? Not too bad? Yeah. Yeah. Yeah, sure. So let's do the ones that are always going to be fixed. What is always going to be the length of the major axis? What is always going to be the length of the minor axis? Perfect. Yeah, and that's true for horizontal and vertical. Now, which one is the major and which one is the minor are what's switching between vertical and horizontal. But the actual value, notice that A is just attached to the major and B is just attached to the minor. In this case, the vertices, it's going to depend. Let's go ahead and generalize our equation and then we'll fill in what the equation would look like for the vertices. When we are trying to move the center, if you've done work with the circle equation before, and again, if we had done a little bit more, the way you go from a circle centered at 0, 0 to a circle centered at hk is instead of x squared plus y squared equals r squared, you do x minus h squared plus y minus k squared is equal to r squared. And so we're just going to do exactly the same thing to our x and y. So instead of x squared, we'll do x minus h squared. And instead of y squared, we'll do y minus k squared. One is, I mean, it's the exact same change. It's the exact same transformation. It's just this is for circles and this is for ellipses. So x minus h. The thing to note here, notice that it is minus minus. So whatever value we see in that parentheses, we are doing the opposite of it for both x and y. Both. That is a statement that is true for both. These equations are the ones that we are focusing on right now, which is for ellipses. The only difference between circles and ellipses are circles are where a and b are equal to each other. Yeah. Okay. So if we have, and this is the part where it gets different between the horizontal. So if we are looking at a horizontal ellipse, which means that the major axis is horizontal, the vertex is going to be located, the vertices are going to be located to the right by the distance of A. So that will be H plus A. And then we're not doing anything along the y-axis, so comma K. And then to the left by A, so H minus A, comma K. So vertices at H plus or minus A, essentially, for our X value. And if it were vertical, we would change the K value instead of the H value. So we would do K plus or minus A to get our two vertices. And then exact same thing with the minor axis, except for the minor axis, we change the Y values if it's horizontal, and for the major axis, we change the X. I care less though about that and more about like just showcasing, like picturing what is happening. So I want to showcase that. I think that's easier to see than just like going through the letters. So let's look at an example. Actually, I'm going to have you guys do this example for yourselves. But I want to establish one thing first. For our equation, x minus 3 squared over 16 plus y plus 2 squared over 25 equals 1, what is our center? Three negative 2 is correct. Opposite of the x, opposite of the y. Okay. Try figuring out your A, your B, your C, and then try graphing this. Yes. Yeah.
It's not, so it would be. Wait, so why is it 25? So it's eight.
I'll go back and double check it, but no, you delete the past. Maybe I will.
C3. That was. If this is an A and B, A, B4, B5, right, so for A.
No, because A has to be.
What'd you guys?
It's A always greater.
Okay, so
So where do?
it's A is 5.
Oh, so is it up and down? Up and down?
I forget something.
Where's
So A and B.
So you go 1, 2, 5. Up and down.
Wait, how is it? How is 8 You're right, actually. That's great.
Perfect. Super.
This is like crazy. This equation. What is it up and down? Is up down like?
Up and down is just vertical. So it's just taking the
So the-
football and just rotating. Yeah, exactly. Exactly.
I knew it.
Yeah.
I was like, I'm not crazy.
Yeah. Can you come, I have a student who's coming in here to.
That's a fantastic question, Joanna. Ignore what I did.
Yeah.
I want 5.
So in this case, does the,
So basically, it's only.
Can't hear you.
it's this distance. Okay, so what does the vertical distance correspond to and what does the horizontal distance? Is A under X or is A under Y? It's Y, so that's vertical. Under X is vertical.
Is this this man?
Yep. There we go.
Yeah.
So you five from the center? or
Yep,
like-
from the center.
Trust yourself.
Oh,
Start at the center and then.
I feel so marked.
Yes.
Okay, why did you put the points? Oh, because the.
Otherwise, that's good.
like the middle.
Oh, it's 4.
Okay.
You're
So when you
different.
get so.
I know. She's holding.
I see. I was.
Is that who you're rooting for?
Yeah, we wanted geared it away,
Yeah.
not three steps. Yeah, I just wanted. It's the.
Yeah,
size.
it's really good. Yes, but it's up and down.
Yeah, it's under Y. Okay, got it.
That's clearly very, I mean, all the talking.
Real.
Yeah.
What was Bearden's score? What's Bearden's score against? Well, it's really good. It's Houston.
Yeah. Oh, I'm so mad, like, we should such a good year.
Y'all weren't locked in with chocolate beds.
Too late, I guess. No, I didn't stay up that late. I didn't even stay up that late.
So all of them was a triangle on the inside.
Yeah, we were undefeated. That was the only game.
Oh, I didn't know. That's why I said.
I just always. I guess this. Yeah, so.
Oh, yeah.
Y'all are like.
Yeah. So we played quarterfinals, one.
So what is this game?
That's just the.
Yeah.
That's not part of the ellipse. So the ellipse is the like black. This triangle is just showing what these both sides. Those are what trace does.
Oh.
So that you don't actually, that's just like what they're there for. That's why they exist.
What are you? I'm fisherman.
I'm about to talk to you. What did we get for A, B, and C? 5, 4, and then 5 squared minus 4 squared is 9. Square root of that is 3. And is this A value, is our major axis going to be vertical or horizontal? This is going to be vertical because it is under the y squared. So this is horizontal. Okay. So let's go ahead and graph this. I need more. So 1, 2, 3, 4, 5, 6, 7, 8. 3, 4. 2, 3, 4, 5, 6, 8. 1, 2, 3, 4. Perfect. If you just put that on the podium there, that'd be perfect. All right, we said center was 3, 2, 3, -2 rather. So to the right by 3, down by 2. We said our vertical distance is corresponding to our A value. So we are going up by 5. 1, 2, 3, 4, 5. Up to this point here, which would be 3, 3. And then down 5. 1, 2, 3, 4, 5 to 3, -7. As our vertices. And then our co-vertices, we are going to the right by 4, 1, 2, 3, 4. Takes me to, what, 7, -2. And then to the left by 4 should take me to -1, -2. And so our ellipse, it would look, if I had spaced my axes a little bit more appropriately, this would end up looking a little more vertical than how it will here. Get something like that. And then where are our foci going to be located? 3 away, and in which direction? So remember, our foci always fall on which axis? Always on the major axis. And so up 3 and down 3 would take us to these foci. So that would be at 3, 1 and at 3, -5. How we get the distance? So the distance comes from a squared minus b squared, and then you take the square root of that. And so that gives us, so 25 minus 16, square root of that is 3. And then in this case, we know that distance is always going to fall on the major axis. So you go 3 up and 3 down. Yeah. All right. Questions with ellipses? How's this feeling? It is new. A lot of weird definitions, but hopefully extracting the information from the equation is pretty easy. Okay, so hopefully the information extraction is not too bad. If that is the case, then the only hard thing about these problems is going to be getting them into that form where we can extract the information. If I'm nice, which is rare, then we're going to be given it in the form just like we saw with the last example. Let's look at one where I maybe not being as nice. This, I'm going to leave your example for you guys to attempt here. I'm pulling another one. There are a lot in the OpenStax book that are like this. So if you're looking for some practice problems, this is a really good place for them. The example that I am looking at, let's pick a good one. Let's do, it's going to look nasty, but it's actually not too bad. This is 64x squared plus 9y squared plus 128x minus 72y minus 368 is equal to 0. Okay. I'm picking a one that looks difficult on purpose because we will find it is actually not too bad. Now, our goal is to get this into the form x minus h squared over either a or b squared, right, over something squared, plus y minus k squared over something squared is equal to 1. I'm going to do a couple of cleanup steps first. The first thing to note, this negative 368 is actually a pretty involved number. It's got a lot of stuff going on with it. I'm not going to go through the derivations to show that it has a lot of stuff going on. I'm just going to ask that you trust me when I say there's a lot of stuff going on with that negative 368. And so I'm going to move it to the other side of my equation for now, just temporarily. So I'm going to add 368 to both sides. And then I'm also going to group my x information and my y information just to separate out kind of like we have in our equation here, make my life a little bit easier. So I have 64x squared plus 128x plus 9y squared minus 72y is equal to 368. You don't need to do this. I just think if you don't do this, it's kind of obnoxious. So I'm going to go ahead and do this. All right. You'll also notice that if I compare like what I have here on my left versus what I have here on my right, we want to get this x minus h squared without a coefficient. Same thing, we want the y minus k squared kind of without a coefficient. So I'm going to try and deal with that here with factoring. What can I factor out from my x's and what can I factor out from my y's to start like moving this towards this? Okay, so from my x's, I can factor out a 64. Let's write that. This is 64 times x squared plus 2x. And then I'm going to leave a little bit of space for myself. And then what could I factor out from my y's? A 9, which is going to leave behind a y squared minus 8y. And then I'm going to leave a little bit of space here as well. What we are setting up for is maybe something that you guys saw in Algebra 2. We are setting up for what is called completing the square. So our goal is to get this x squared plus 2x plus something to match in such a way that we can essentially factor it down into an x minus h squared. And similar with the y's, we want to get that into something that we can then factor into a y minus k squared. Now, the way that we can figure out what this something should be, we're essentially just missing a something here. What is it that we need here? This is the completing part of completing the square. To look at that, I'm going to take a look at these actually multiplied out, this x minus h, this y minus k. If I do x minus h squared, I get x squared minus 2hx plus h squared. And if I do y minus k squared, we get y squared minus 2ky plus k squared. So the thing that is missing in red here, I need to add in an h squared into this box, and I need to add in a k squared into this box. But I don't know h and k yet. The good news is, though, h and k show up elsewhere in this setup. Specifically, my linear x terms coefficient is -2 times h, and my linear y terms coefficient is -2 times k. I'm going to keep going. Therefore, what are our values of h and k? So taking this coefficient, dividing it by -2, I get -1 for h. And -8 divided by -2, get a k value of 4. Because you'll notice that in our equation here, the coefficient in front of x is -2h, and the coefficient in front of the k is, or the y is -2k. So if you divide it by -2, that'll tell you what h and k are. Okay. What then am I missing to fill in these red blanks, to fill in the blue, to fill in the pink? I'm missing the squared versions of h and k. So if h is -1, what is h squared going to be? That's just 1. And if k is 4, what is k squared going to be? 16. So into my blue, I need 1, and into my pink, I need to add 16. Now, I've added those in on my left-hand side. If I've added those in on my left-hand side, what do I need to do on my right-hand side? Exactly the same thing. Here's the trick, though. I didn't actually add 1 and 16. When I put 1 into that blank, what did I add to the left-hand side? 64 times 1 is what I added to the left-hand side. And so I need to add 64 to my right-hand side, coming from this 64 right here. And when I put 16 in to my pink blank, what did I actually add? 9 times 16, which is 144. And so, having completed the square, I get 64 times x minus h, which is x plus 1 squared, plus 9 times y minus k, that's y minus 4 squared, is equal to, in this case, 368 plus 64 plus 144. I get that this is 576. And from here, it's just the exact same example that we did for part 1 and part 2. Carson, what do we do from here? Divide by the 576 on both sides, and then you can use that to figure out what your A and your B are. And then graph. So the only hard thing, the only new thing here is this completing the square process. And then we've got this kind of obnoxious element here where maybe adding what I want to add on the left-hand side is not exactly like what I am. It's being messed with, right? So we have to be careful. All right.
In the process of throwing my bag.
Oh, it is.
What is due on Sunday? We've got progress checks and the WebAssign